Hello everyone, welcome to the Geek Netter. In this episode, we are talking to Ankit Sultana, who is a staff engineer at Uber and has several years of experience contributing to Apache Pinot, real-time analytics, and producing business impact at Uber. In this episode, we are going to dive deep into Apache Pinot's architecture, ingestion, query processing, and discuss some of the interesting concepts. I'm sure you're going to like this discussion. If you do, please hit the like button, share it with your network, and subscribe to the channel. It means a lot. Also, if you have any further questions, put those questions below in the comments, and we will do another episode with Ankit talking about some other advanced concept, and we'll make sure that we address those questions in that episode. I hope you enjoy. Thank you. Hey Ankit, so great to have you today. I'm also excited that we are going to talk about Apache Pinot and understand the architecture, ingestion, query processing, and all the amazing things you have been doing with Apache Pinot. We'll take an example, try to understand how it works. So really excited, and thanks for joining. For our audience, let's start with a little bit of introduction, what you have been doing, how you're related to Apache Pinot, and what are we going to talk about today?
Yeah, thanks for having me, Cavalia. I've been following the podcast for a long time, and I must say, I think this is one of the more unique formats where systems people just can talk about the deeper innards of the databases and systems they're working on. I think a lot of other podcasts are usually high level, so this is I'm always looking forward to the next episode. So it's good to be a part of this. But yeah, for the audience, I'm Ankit. I've been a staff engineer at Uber for a while now. I've been working there for almost 7 years. And there I've been part of the real-time analytics team. We essentially own a platform built on top of Apache Pinot. And I joined that team around 3 years ago. And from there on, I found opportunities to work on Apache Pinot and also show some business impact at Uber. And over time, it just kept on working. I kept on adding features. I found ways to build new features in there, like time series engine, multi-series engine features, and so on and so forth. And which brings me to today, which is I think right now I'm also serving as one of the PMC members of Apache. So what that means is that we are looking for opportunities to improve the technology a bit further, take it even further in this OLAP domain. And I think I think most people would be familiar that OLAP used to mean aggregation queries almost 8 years back. I think at least in the last decade, everyone used to think, okay, OLAP means select count star, group by kind of a thing. But these days, OLAP can pretty much do everything. I think today, OLAP just means low latency. So anything low latency is what Pinot is good at. And so yeah, I work at Uber, but I spend a lot of time working on open source features. And yeah, that's pretty much about me.
Perfect. Yeah. And it makes me more interested because you talked about real time, low latency, how analytics has changed. And Apache Pinot is a great technology, and I've also used it in production, and I loved it. So would be nice to start with the basics, right? Because it has changed. The technology is evolving. A lot more features have been added. So let's start with understanding what is Apache Pinot and a bit of high level architecture, so we can make sense of whenever we go deeper into certain aspects of it.
Yep. So I'll start with a very historical kind of a quick primer about where Apache Pinot started. So it started at LinkedIn, and this was I think back in 2016ish. I was in undergrad at that point, so I pretty much know knowledge about it. But I know that much that at that time there weren't a lot of OLAP systems which were open source, and I think this is something that people often forget that ClickHouse, Apache Pinot, and all those things are pretty recent, and they started gaining popularity in the late 2010s, so 2019, 2018ish kind of a time frame. And I think at that point, ClickHouse also started. They started talking publicly about it, and finally the company also formed. On Apache Pinot side, Uber was one of the big adopters of Apache Pinot, and then the company Startery, which is a startup based on Apache Pinot, they also started I think around 2019ish kind of a time frame. And from there on, today, real-time analytics has become it's a very commoditized. At the same time, it's also evolving at the speed of light. When I say commoditize, I mean that real-time analytics can be supported with like just open source tech. You can essentially take all the technology that is there in open source, just run it in your on-prem setup, and you'll have like a state-of-the-art system running on your private environment. So that is where we are today. And Apache Pinot, like what it essentially is about is you want to be able to ingest data in real time. So we are talking about like, let's say events are happening and they are being published to a Kafka topic. You want to ingest them to a database where it gets continuously appended upon, where essentially like every record in your Kafka topic gets appended to a logical table in your database. And separately, you want to like query that data. So think of like SQL queries running. So one quick example could be like, let's say I'm getting like, this is like an Uber themed example, and all the examples I'll use today are like hypothetical. Of course, like I don't want to like share anything internal. So just hope like no one takes a conclusion that, okay, that Uber does this explicit, like specifically in their systems. But let's take like an Uber kind of example where you have trips happening and I want to append all the trip events to a SQL kind of a table. What if I have like real-time freshness of this data? Then I can like select count star queries where event time greater than some now minus 30 minutes. And that will give me like the number of trips that have happened in the last 30 minutes. And then if let's say your events are very wide, let's say you have a bunch of attributes in there. Like for example, let's say you have user UID, you have the Uber product code like UberX, Uber XL, and so on and so forth. You have the trip amount, you have the user UID, driver UID, city ID, and so on and so forth. Then you can slice and dice this data. Like this data keeps on getting appended to a table. And you can just keep on running queries to figure out, okay, in the last 30 minutes, for example, in this particular city, how many Uber X trips were there? Or maybe in this particular city, you want to track like how many cancellations were there, and so on and so forth. So uh, real-time freshness with low latency queries can power like end user facing use cases, as well as they can also power like alerting use cases, observability use cases, and so on and so forth. So Apache Pinot, like when it was started, like, it was mainly started for like end user facing kind of applications. And that is where the latency thing also started. So I think there's like this common fact which is talked about that human perception, like we perceive something as instantaneous when it's between 50 to 100 milliseconds. And that is where the query latency targets also started coming in. That if your queries can finish in under 50 milliseconds or so, and those are, let's say, analytical queries like graphs loading in your analytics dashboard, for example, in Google Analytics, let's say, then if it's taking like 500 milliseconds, then the user perceives like there's like some lag here, and there's like some heavy computation being done there. Versus if it were loading in less than 100 milliseconds end to end, then that means that it's from users' perspective, it's like pretty instantaneous, and they don't even think about that there's like some data being loaded or some expensive computations being done in the background. For them, it's like a very intuitive system. Like you just click a few buttons, and let's say I want to get more answers, I'll get more answers very quickly and almost instantaneously. So yeah, low latency queries for end user facing applications with real time ingestion of data is where Pinot started. And over time, it just kept on taking on more and more use cases. And another one last aspect, which I'll probably call out, is at the time, there was also a lot of talk about Lambda architecture. So Lambda architecture is essentially like you have this real-time serving stack, and you also have a batch pipeline alongside it. And Pinot also supports this using a hybrid table concept, where essentially what you can do is like, let's say I have my drip data again, and I want to store the last 5 years of data. And maybe I'm using like a Kafka topic for getting the real-time feed of the data. So I'll create like a real-time table out of it. But my Kafka topic will have like a finite retention, right? It won't have like a 5-year retention. That is not tenable at scales, at higher scales. What you end up doing is, okay, for my real-time table, maybe I'll keep like a 7-day retention. And the older data, I'll backfill it through some source of truth, Hive data set or Snowflake data set or Databricks data set or what have you. So that is also something that Pinot started out with. I would say like hybrid tables have become like kind of like niche at this point, but that was another idea that was quite talked about back then. It is still being used, but not as vigorously as some of the other features that we ended up implementing later on down the line.
Perfect. Yeah, and those are very interesting and powerful features and probably in need of all the modern applications that we have. As you mentioned, if there is more lag, it feels really, slow and the user experience is not great, and that kind of impacts the adoption and retention of customers. So would love to see how Pinot powers all of that: ingestion, predictable latencies, and the different types of queries. You also mentioned wide column tables or data that is growing, and so on. So why don't we start with like a high level architecture, like just drawing some boxes, understanding how does it even look like, and some of the design decisions, and then we can dive deeper into the example that you mentioned.
Yep, sounds good. So I think what I'll start with is we'll talk about the different components and what their responsibilities are. We'll also talk about like how data usually flows into Apache Pinot and how you usually query it. So the first concept at a high level is, so Pinot has this component-based architecture. I recently learned that this is a common strategy that LinkedIn also does, but don't take my word for it. But it kind of like reflects like LinkedIn's root is what I heard from someone. But so when you're designing system, there is usually like, okay, can I do everything in a single system, or should I like have separate responsibilities for the different components involved?
Yeah.
But Pinot goes with like a component-based approach where we have this concept called Pinot servers. Then we have Pinot brokers, and we have the brain of the cluster, which is called Pinot controller. And finally, we have the minions. So Pinot servers are the ones which store the data. I'll talk about minions probably later on because they are like the auxiliary component of the system, but these are the minimal required components of the system.
Yeah.
And Pinot also has a dependency on Zookeeper. I think this is often like frowned upon, but most distributed systems end up having a dependency either on Zookeeper or they go with like their own Raft kind of an implementation.
Yeah.
Like I think for context, like ClickHouse also started with Zookeeper, but then they implemented their own ClickHouse Keeper because of performance reasons. But anyways, so Pinot
Also
has this
Kafka
like
did. Yeah.
Kafka did, and then they went with Kraft
Yeah.
recently. So yeah, Zookeeper is like the distributed coordination kernel. I think for folks who are not quite familiar with how Zookeeper works, like essentially it's like a distributed system where it gives you like primitives where you can have like a config stored in there. At the same time, you can subscribe to events. For example, if let's say there's something going on in a given particular, so Zookeeper stores data in like a tree kind of a structure. If let's say I change a particular node, then you can subscribe to events on that particular node across your any of your Zookeeper clients, and you can take actions based on that. So Zookeeper acts like our distributed coordination kernel. So that way Pinot doesn't have to like explicitly implement like all the consensus kind of things within it. And it makes it allows us to focus on core database kind of problems rather than the consensus problems that are usually there.
Yeah.
And another thing to call out here is that we don't directly use Zookeeper. We do use it for some things, but there's another library which was again built by LinkedIn, which is called Apache Helix. It is a library. It can also be run as a separate service kind of in a service kind of a mode. But essentially, what it is like it gives you a layer on top of Zookeeper, because Zookeeper doesn't have a concept of clusters or participants or spectators or what have you. Zookeeper just has, okay, I have watchers, I have a Z-node kind of a tree and stuff like that. With Helix, like you can say that, okay, I have a cluster concept, then I have participants in that cluster, then there's like a controller role in the cluster, and there are spectators in the cluster, and so on and so forth. So it allows you to build like a distributed system where the system doesn't need to know about the Zookeeper innards, and it can just operate on like logical concepts of or constructs of participants, spectators, controllers, and so on and so forth. So it essentially allows you to like model a cluster kind of a topology on top of Zookeeper.
Yeah. So Zookeeper
And
is like more like a lower level primitive, and then Apache Helix helps you to model it in a very high level manner in terms of your system and clusters and all of that, which makes it easier to talk to Zookeeper, right?
yes, and so one concrete example I can give here is I think if someone is like trying to imagine this, you can think of like Apache Helix as like a class, and within that there's like a Zookeeper client in there as one of the member variables. And what concretely like it allows us to do is like you can, for example, for a segment state transition. So segments are files in Pinot, and they can go from like a consuming state to a online state to an offline state or a drop state and what have you. So what it allows, what Helix allows us to do is we can define what states the segment can be in. So we can explicitly say that the segment can be an online state or whether it can be an offline state, and we can define like a set of states. Then we can define like when it is going from one state to the other state, what should be done as part of that. So for example, let's say in a Pinot server, I receive a transition which tells me that I have to go from a consuming state to an online state. Then that triggers like a certain core path in Pinot where we take care of like committing the segment or replacing an in-memory segment or whatever the business details are. So that way, like it allows you to abstract out the coordination part with just the business logic of your data.
Perfect.
So it gives you like a state machine kind of a thing on top of Zookeeper. But
Cool.
yes, yeah, this is the high level, super high level architecture. Now let's dive into like Pinot servers and what they are. So one really good thing about Pinot is that you have like tenancy concept right out of the box. And this is very important because like, for example, let's say I'm running Uber, right? And Uber has multiple products like Eats, Freight, Rides, and etc. etc. So I wouldn't want to like host everything in the same cluster or in the same tenant. Maybe I can put everything in the same cluster because I don't want to have like multiple controllers for them. But what I can do is like I can have like a single cluster, but I can have multiple tenants within it. And I can assign like use cases to tenants, or maybe I can assign use cases based on like the business vertical to specific tenants. So that way, like if let's say Eats is having an outage, that doesn't mean that Rides also needs to have an outage, for example.
Yeah.
So that is there from the beginning. And for this particular demonstration, let's assume that this particular 4-node setup that I'm showing, all those 4 servers are in the same tenant.
One question though. So as you mentioned, and this is a really powerful feature as you talked about tenant and for isolation purpose. But is it like in the entire stack? Like also Helix knows about these tenants and controllers knows about these tenants, or it's just about the Pinot servers?
Yes. So Helix does know about the tenants, and the way this is done is like Helix has this concept of like instance configs, and we essentially have implemented tenants using a tag-based way. So, for example, if let's say I start with like a vanilla cluster, I bring all 4 servers up. Right now, there's no tenant in any of the servers, so there's like no tenant anywhere. Now, when I am going to create a tenant, I actually don't create a tenant which creates like servers within it. What I do is I go to a server and say, okay, that in its server level config, add this tag, and the tag would be something like, I'll write it here. So the tag is a list, and it can be something like eats underscore real time, and I can also put in eats underscore offline. So this means that for my eats tenant, I want to have both real-time table as well as offline table in this particular server. So that essentially also creates a tenant. So it's a tag-based concept. So that way servers define what tenants there are, and Helix knows about the instance configs, which are the tenant tags. And throughout our state transition kind of a logic and instance assignment logic, we take that value in to figure out, okay, for example, if let's say a new table comes in, then I can go to Zookeeper or Helix to figure out, okay, give me the servers for this particular tenant tag, and then I can use that information to figure out the data assignment, and then from there on things happen.
Makes sense.
But yeah, so essentially we have this like tenant concept. In this case, let's say we have this each tenant. So each of the servers, and let's say I create a table. So my table can be like I talked about, it can have like wide events as well. And by wide events, I mean that essentially the data is denormalized. So we put like all the columns in there. In this particular example, actually, let me take the rights example because it's easier to explain that. Yeah. So let's say I have the trip ID as one of the columns. Then I can have the amount of the trip. I can have the driver ID. I can have the user ID. I can have duration, pickup point, drop off, and so on and so forth. So this can be like a very big list. And again, like these are just hypothetical examples we're using to understand. So don't assume after like watching this video that Uber is actually literally storing.
Yeah. Okay.
Yeah. So
it's a little disclaimer.
Yeah. I just want to be clear because I think what I often see is that I think on LinkedIn and other posts, there are often like incorrect claims being made, even about our systems. I usually refrain from engaging there, but it's something just wanted to be explicit about it in this case. You can also put in like JSON blobs in there. So let's say you have like some, I don't know, experiment JSON data. The experiment is, let's say, the configurations that were enabled for this particular trip in your backend. Maybe you want to dump that also in there. So you can dump everything in there. So this will be your table schema in your Pinot table. So for real-time ingestion, Pinot only supports Kafka, as in like any stream, any distributed messaging queue. Most prominent is of course Kafka, but there is also like Kinesis and a bunch of others that I'm sure others are using in production already. But I'll keep on saying Kafka because Kafka is now the most popular one. But this can also be, for example, a Red Panda stream.
Any Kafka implementation, basically, right?
Yes. And essentially, like what we need from the system. So Pinot again has interfaces throughout its layers. So we have like a client and a stream message consumer implementation. And as long as it can implement constructs around like persisting offsets and consuming from specific offsets, then like you can just replace it with like any distributed messaging queue and it should be pretty seamless to use it. But let's say my Kafka pipe is called trip events. This can have multiple partitions. Just a primer there, like let's say this is my topic. So your topic would usually have partitions. You don't directly consume from the topic. Topic is like a broader concept. The actual data is in partitions. And let's say in this particular example, keep it simple and keep only like 2 partitions. So each of these partitions, like producers will be publishing to them. And one of the consumers will be Pinot. Other consumers can be like your ingestion pipeline to batch sources or any like business logic as well. So that is another good thing about Pinot, and that is where the Pinot really is like an add-on in a system where you're already very reliant on like messaging queues for a business logic. And if let's say you already have like a decent Kafka footprint or a decent Kinesis footprint in your architecture, then Pinot fits in pretty seamlessly there because you would already have like event queues in there or event topics in there. And you might be already using them for a business logic for triggers, or you might be using them to ingest into batch sources. So with like Pinot, you basically like without any external processing required, Pinot can just pull data from those existing event topics just by you creating a table and telling Pinot like where to like pull the data from. So that way, like you can essentially like also have a real-time analytics layer on top of your already existing stream messaging layer or whatever you have in your system. So yeah, we have partitions in there. Partitions will be like essentially like receiving a bunch of events. Pinot consumes from them. And that is one cool and important thing to understand is that Pinot pulls data for its real-time ingestion. This is different from the push model that ClickHouse and some other databases have. And Pinot will essentially, what it will do is, like, if let's say I have a replication factor of 2 for this particular table, then, and let's say this is partition P0, this is partition P1, then I will have consumers. And there are different assignment strategies here, but one of the simplest one to understand and even use in production is that just spread your consumers in a mirrored fashion across the servers that you have. So, for example, in this case, if I have a replication of 2, then I will have 2 Kafka consumers across 2 different servers. And this is my replica group 1, and this is my replica group 2. So what will happen is that when you create a table, Pinot will first figure out, okay, what is the latest offset in this particular Kafka topic? And there are settings for that. Also, like, you can choose to like consume from the oldest available offset or from the latest available offset. The default is the latest. But if let's say I onboard this table, then I'll start consuming from the latest available offset. And then Pinot will start consuming this server, the one on the leftmost server, will start consuming partition P0 from the latest offset. And this server again the third server from the left will also be consuming from the same partition. And before they start consumption, Pinot's controller will figure out like which offset I wanted to start consumption from. So that is already predetermined. And when we create the mutable segments, we call them mutable segments, which mutable segments are essentially ones which are buffering data in memory. And after a certain time, they flush it onto disk. So when the mutable segments are created, they know precisely which offset they're going to start consuming from. And they'll continue consumption until a certain threshold of time or size or row count is reached. So I'll pause here, like, if you want to, like.
So basically, based on the number of partitions you have, so who decides like how many? So let's say I have 2 partitions in this case. So who decides that I have to distribute this data across n partitions or n partitions in Pinot servers and not the Kafka servers? So, and what is the correlation? So if I have, let's say, 100 partitions on my Kafka topic, how does that get distributed across the Pinot servers that I have?
Yes. So when you create a table, you will be specifying multiple things. So one of them, the first one is the replication factor. And the replication factor is, in this case, for example, it's 2. So with the replication factor, what we'll do is like, okay, let's say, and you will also specify the tenant name. So in this case, I'll say that for my real-time table, the tenant name is rides.
Yeah.
So first thing Pinot will do is, first is figure out which servers are eligible for this particular table. So for that also, for every layer we have configurations. Like, so essentially, like, every layer can, like, every decision can be customized. But I'll take the most straightforward example, and which is also the most common example. So we take the rights tenant, for example. So you requested 2 replication factor and rights tenant. Pinot will first figure out which servers are applicable for this particular request. So it will figure out, okay, I have 4 servers available in rights. My replication factor is 2, and my partition count is 2. So actually, the partition count doesn't even come here. Like, I'll just look at the replication factor to begin with and think, okay, I can just use all of these servers and I can distribute them into like 2 equal halves. And if my number of partitions, as long as the number of partitions is greater than the number of servers in each replica group, then I can just completely utilize the replica group. Otherwise, I can reduce my replica group size appropriately and just use a subset of the servers in there.
Okay.
But in this particular example, let's assume that we always have like more Kafka partitions than the number of instances in a given replica group. Then what we do is just like simple modular arithmetic. So once you figure out the replica group, which is a distinct set of nodes. So in this case, like there won't be any nodes common across the replica groups. Replica groups have to be completely disjoint. And then you will just like use modular arithmetic to like assign partitions to servers.
Yeah.
And one thing you do here is you assign them in a mirrored fashion. So when I say mirrored, what I mean is that each replica group, like within each replica group, you'll assign integer IDs to the servers, so 0 till n minus 1 or whatever. And the same would exist across all the replica groups. And if let's say a given partition, Kafka partition, is on replica group 0 with server ID 2, then it would be on replica group 1 also on server ID 2. So that is how like we do like mirrored kind of assignment. Although like this is also configurable, so we also have knobs here to change that behavior. But this is the most intuitive and common behavior that we use.
Yeah, that sounds good. And it's like replication is happening in real time in parallel, and since they both the servers hosting P0 partition, they are consuming from the same partition, so they need to also have separate consumer groups. And I believe it is done by the number that we give to each of these servers, right?
Yes. So that is an interesting point. So what we do in Pinot is that we explicitly track the offset that we are consuming at ourselves. We don't rely on Kafka for it. And so because when we create a segment, let's say we created the P0 segment, the mutable segment, Pinot will know exactly which offset it is going to start consumption from. And then a consumer starts at that particular server for that particular partition. And it will start consuming and it will continue consumption until a threshold is hit. Once a threshold is hit and we decide to commit the segment, then we'll figure out, okay, let's say I started consumption from offset 100 and I finished at offset 200. Then I know that the next segment will start from offset 201. So then we create the next mutable segment, and the next mutable segment will know that, okay, I have to consume from offset 201. So we don't even really need the Kafka side features there. The only feature we need there is if I can give you an offset, just send. You should be able to like send me the records from there on, and I should be able to go back and forward in time. So let's say, for example, let's say my server, this particular leftmost server is consuming, and we had only consumed until offset 150, and I restart the server. So what will happen is that when I restart, then there will be like a segment transition which will happen from offline to consuming. Offline to consuming because the segment will start in an offline state because Pinot will recognize, okay, the segment is no longer live, and it is expected to be in consuming state, so we'll trigger like an offline to consuming transition, and as part of that we'll create a consumer, and we'll use the offset that we knew that, okay, we have to start consumption from offset 100, and we'll go to Kafka again. We'll request like, okay, start sending me messages from offset 100.
Oh, okay, I think that makes sense. One important point that I would like to clarify, like what exactly happens there, since you are maintaining the offset, right? And Kafka may have duplicate events as well. So how does idempotency work here? How is it important in this context? Just let's talk about that a little bit.
Yes. So I think most people would know, like, I think usually what you go with is like an at least once kind of a message delivery semantic. Exactly once is super hard to achieve, although it is possible, but it adds like a lot of a bottleneck to your ingestion kind of a pipeline. But if let's say you have duplicate events in Kafka, duplicates will be ingested into Pinot. But Pinot has features which, for example, we have this deduplication feature which allows you to like deduplicate data based on a given primary key. We also have an upsert feature which allows you to like keep only the latest version of the record for a given primary key. So we have features to guard against that, but at least in a mature stream processing system, the rate of duplicates should be very, very low based on our experience. And I would say like if you're seeing a lot of duplicates in your messaging queue, then you should probably look at the infrastructure layer. Ideally, they will exist, but they should be less than, I would say, 0.01% or something like that. But to answer your question, like if let's say there are duplicates in the Kafka topic itself, we will end up ingesting those duplicates. They will color the queries. But to work around that, you can use the deduplication feature or the upsert feature in Pinot. But ideally, like you should be making sure that the topic itself like is like your distributed queue should be like resilient to this, and it shouldn't be like, for example, having 1% duplicates in your producer pipelines. That would mean that there's like an issue there.
That's fair. And if we are trying to solve the problem of duplication at a wrong place, it's also a wrong strategy, right? If the duplication is happening at your Kafka layer, you should probably look into that. But it's good that we have some deduplication features for the 0.01%. If there are some systems that are not really resilient or, let's say, not really tolerant to duplication, so you can use that at certain cost, I believe.
Yep.
Okay. Let's move on.
Yeah. So I think because you're halfway, I'll just wrap up the one final point about ingestion, which is, I think, probably the most interesting one, which is that, like, I think I talked about like how mutable segments are there and how after a certain point of time, they transition to an immutable segment. So let's talk about a given partition. Let's zoom into a given partition and let's look at the segments there. So what will usually happen is, if let's say my table name was foobar and my partition is P0, then my segments will look something like this. So I will have foobar P0, 0, then the next segment would be just incremented by 1. So we call the trailing integer the sequence ID. And until, like, let's say it's X.
Yeah.
And X is the latest segment in this particular, for this particular real-time table. Now, and this particular partition. When we have a setup like this, in nearly all cases, I say nearly because we recently added more features where this is not strictly true. But in nearly all cases, all of your segments before X would be immutable segments. And essentially, immutable segments mean that the segment has been committed as a file to disk. It has been copied to a remote store like S3 or HDFS for durability and resilience. So, for example, let's say you lose all your servers, right?
Yeah.
As long as your data in your S3, the cluster can come back up again. It will re-download the segments from S3 or HDFS, and it will be able to like consume from where it left. So all of these would be like immutable segments, and the latest one is the mutable segment. And the reason this is quite interesting is because from an architecture point of view, like Pinot doesn't have a write-ahead log. Because Kafka is a write-ahead log. Kafka is a distributed write-ahead log. And what that means is that I don't need to, if I'm getting data consistently, I can just choose to buffer it in memory and index it in memory. And Pinot is like a Java process. We do something off heap. We don't do this on heap for most of the indexes. Most of the indexes are off heap completely. So we can choose to like buffer the data in memory and index it in using like in-memory structures. And let's say like there was like a server restart or a server crash, then we can just rely on Kafka as a write-ahead log. And as long as we know like, okay, I can just resume consumption from a certain point of time, then I'm good.
Yeah.
So this is different from, for example, ClickHouse. Like what ClickHouse requires you to do is like you have to create batches of records, and you push those batches to ClickHouse will write them as a part in its internal and local storage system. And as you can imagine, like if I want like real-time ingestion, then I'll have to keep on publishing these parts like almost like on a second kind of a resolution, or maybe like a few seconds of resolution. So that means that I can end up with like a lot of small parts. And that is where the ClickHouse's LSM tree structure comes in. That you keep on pushing these small parts, and ClickHouse in the background will just keep on like merging these parts in the background. But in Pinot's case, like because we already have a write-ahead log, what I can choose to do is, okay, I can have like segments open for like almost a day. So for a day, this mutable segment could exist without committing and converting to an immutable segment, and I can just keep on indexing in memory. And maybe after a day, I just choose to, okay, like flush this and start with the next mutable segment. So that is one
But
key
it
design.
stays in the memory, right? So there is some relation to how much memory you have left.
Yes, but because it's off heap memory, so you're not strictly bounded by the physical memory that you have. And the other part is that usually, like, we also have a size threshold. So if you have like a lot of data, then it is recommended to like flush it to disk.
Yeah.
But it is even for like very high scale scenarios, you can keep a mutable segment open for a long time. And that comes down to like the fact that Pinot, like if let's say for example your data is like dictionary encoded and it is like you have like some high cardinality columns, but they are not that many in number, then dictionary encoding and other things like can make sure that your data size and footprint on memory is like pretty low.
Okay. One last question here before we move on. Why is it important for me to keep the mutable segment longer? Just because it may be useful for me to mutate data, or is there any other thing?
Yes, that's a good question. So there are actually that is a very because of the recent features now the advantages of this has grown quite a bit. So one advantage of keeping a mutable segment for long is, let's say my Kafka retention is 7 days, right? If I keep a mutable segment open for a day, that does mean that when I restart the server, I will have a very long catch up to do. So I'll have to start from a day before, because like latest Kafka offset that I haven't consumed is like 1 day old. That will reconsume that entire data. That will put pressure on your Kafka topic. And that will also mean that Pinot has to do more work when it starts up to catch up to the required offset. But all of these things depend on scale. So if your scale allows for it, then you can just keep it. And the advantage of keeping this could be that you don't end up with like a lot of like small segments. And that has direct implications in like query performance. But Pinot also has features where if let's say you are consuming or committing very quickly, let's say I'm committing every 1 minute or so, and I have a very long retention table, let's say 1 month. So another thing is that it is common to have like a real-time table with a month retention or 3 months retention even, and even like even longer than that. But if let's say I'm committing my segment every 1 minute, that would definitely lead to a lot of segments. So one option is, okay, I'll just keep my segments open for a longer time, maybe an hour or maybe like 6 hours or something. Another option is that I can continue committing them quickly, but I can use like a minion task to merge the smaller segments in a separate component. So that is where the minions come in. We didn't document them here, but they are like a separate installation of separate set of nodes. And what they allow you to do is like run tasks like the merge task or the compaction task and the other things.
Okay, sounds good.
But yeah, I can jump into the query side of things maybe now.
Yeah,
So
I think it makes sense.
So yeah, the query on query side, we again like has a ton of features. We have the single stage engine, the multi-stage engine, and we recently added the time series engine last year. And it is marked in beta right now, but we'll soon graduate it to production ready, probably with the next release itself. But I'll talk about like what the individual engines do, but maybe I'll start with like the first engine, which is the single stage engine, which is what used to exist in the original Pinot design, and which is what made like Pinot very popular in the early days. So the single stage engine, what it is like, so in Pinot brokers also like you have the concept of tenants. And in this case, I'll assume that the tenant that I have is again like maybe like rights tenant or some other tenant. So another thing is that you can mix and match tenants. So for example, if let's say my broker tenant is A, my server tenant is B, then I can create a table where my broker tenant is A and server tenant is B. It doesn't need to be that my broker tenant has to be named rights here, for example. But anyways, that small detail aside. So let's say I have this rights tenant of Pinot brokers here. The usual query flow is that you submit like an HTTP request with a SQL query to Pinot broker. Pinot broker will choose which servers to query for that particular SQL query. And the way it does that is by figuring out, okay, for the query that you are running, which segments and tables are going to be hit from it. And we just find out a subset of servers that can serve that particular query. So for example, in this case, the simplest strategy could be that I just route this to, based on replica groups, I just route this in this way. I think I ended up moving this. So simplest strategy can be that my broker always like scatters to a given replica group. And that way I have isolation across replica groups. But if let's say my this server was down, let's say the server hosting P1 was down, then Pinot will automatically switch to the mirror server in the other replica group. So those features are all there. And again, there are a lot of details here, but at a high level, this is what's going on. But the key thing to understand here is that we are doing like a scatter gather query here with the single stage engine. And that leads to like a lot of performance optimizations and simplicity of the architecture. But it also leads to like limitations on what you can run with this kind of a design. And when Pinot started, at that point, I think we didn't even have like a calcite integration there. So all of the planning, the parsing, and planning on servers, operators on servers, everything is like custom made for single stage engine. So you can think, and the kind of queries that single stage accepts have a very fixed format. So we essentially only accept queries that look like this. This where is optional. Then you can have a optional group by, you can have an optional order by, limit. And limit also allows you to like set offset. So limit and offset. So this is the only query format that Pinot will accept. Pinot's single stage engine will accept. And this means that our query planner becomes very simple, because if I don't have to support like general SQL, like derived table, CTE expression, or what have you, then your query optimizer can only focus on like simple optimizations. And I don't have to focus on, for example, like reordering project over a join, or reordering filter and project order, and reordering joins, or even like a ton of other optimizations.
Yeah.
So that means that we can just get by with a very basic optimizer. And the way it works is, if let's say I have a query with just a group by, limit, I think limit is anyway easy to understand, but I'll remove it for this particular example. So a query like this will correspond on the server side. What will happen is that we will compute the aggregation based on the group by that we have set. And we'll of course like add the filters to the query. Whatever results we'll get, those will be partial, because those are computed within the server only. So we'll send this like partially aggregated result to the broker, and broker will run like a final reduce step to aggregate data across the server and return like the final result back to the user. So that is the scatter gather, a broker reduce kind of a design. And if we zoom down within servers, the operator structure looks something like this. Maybe remove this. So at the lowermost level, we have the filter operator. Then above it, we have something called as a doc ID set operator. Above it, we have the transform or project operator. And above that, we have custom operators, which are bespoke for the query shape that we are currently playing with. So the bottom three are like kind of constant. They are always present for every query. And I think you can imagine pretty easily like what each of them are going to do. Like filter operator, and these operators are run per segment. Yeah, actually, let me also talk about that at a high level first. And this is, we are zooming down into a server right now.
Yeah.
So at a server, you can assume in the simplest case, I will have a single combine operator, which will combine results across segments. And for each segment, I will have an operator chain, which will look something like this, for example, for a group by query. And the bottom three operators are common. So the filter operator will essentially execute the filters and return like a bitmap to the layer above, telling that, okay, these are the particular docs which match my particular query. Docs means rows for folks watching, but yeah, filter operator returns like a bitmap to the doc ID set operator. The doc ID set operator like converts the bitmaps to an integer array of a given chunk size. So that way, the rest of the execution can choose to be chunked if it wants to be. Then my transform project operator will either materialize the column per column data that we are reading. Like for example, in my select clause, if let's say my table has like hundreds of columns, but my select clause only has trip ID and maybe let's say a sum amount thing. Doesn't make a lot of sense, but let's say we have this. Then I will need to read data from trip ID and I will need to read data from amount. And Peter is smart enough to know, okay, that I need to materialize this particular thing immediately, or maybe some things I don't need to materialize at all, but I just need to initialize the pointers to the data so that the rest, the whatever is the operator above this can just use that as an abstraction and get the data in like a generic form. So this basically just wires all the columns that we're going to read in a way that the operator above it can consume it. And operator above it will either consume the entire rows that match this in this particular segment, or it will process data chunk by chunk and early terminate if it can. And there is like a lot to be discussed here. Like the number of actually one thing which we haven't been good at in Pinot is talking about the optimizations there are already there in Pinot. I think, for example, I think one of the things I also saw like Data Fusion also talked about a similar kind of an optimization a few months back. So one of the optimizations that already exists is, let's say I am doing a group by on city ID, and this is my select city ID sum amount kind of a query. And my city ID column, because city ID, as you can imagine, has low cardinality, so it makes sense to like use dictionary encoding for it. And what dictionary encoding does is it will essentially like convert your sorted list of cities. So let's say we have Amsterdam, Chicago, or San Francisco. It will convert them to integer IDs, 0, 1, and 2. And this essentially allows us to like use inverted indexes. It also allows us to do, for example, if let's say I'm doing a group by and my data looks something like this. Let's say my data, let's say I have like millions of rows in a segment and all belonging to just these 3 column values. The first one, for example, could be Amsterdam, then SF, then Chicago, then SF again, Chicago again, and so on and so forth, then Amsterdam again, maybe. So if I figured out, okay, these are all the rows I have to read, if during my group by, if I start reading all of them individually, then that is like pretty inefficient, especially for, this is like still like a lower length column, but there can be columns like UID, for example. UID is like much bigger than a usual city name. It is like usually 36 bytes in the string format. So if I start reading those and they're repeated, then it's just like wasteful work. So Pinot is smart enough to know, okay, that if I'm using a dictionary encoded column for my group by key, then I don't need to read this. What I can just read is simply read the dictionary ID values. So I'll read like 0, for example, I'll read 2 here, 1 here, and so on and so forth. And I can just use that for my group by, compute the entire group by just using this, because I'm doing like a sum on amount here. So I have to read amount, the exact value here, of course. So I'll compute that aggregation expression per grouping key. And later on, I'll convert my grouping key to the corresponding actual value. So Pinot is smart enough to do that already. But yeah, these are optimizations I think which we often don't talk about enough. There are a ton of such optimizations in Pinot. But so yeah, we can compute like group by efficiently and return a result to the combine operator. Combine operator will merge these across the segments. And combine operator will return like a single chunk back to the broker. And broker then merges results across servers. So that is how an entire single stage engine query works. We are short on time, so I'll just very briefly cover what the other engines that we have are doing. So this was a single stage engine. This is very good at scaling. So this can do like thousands of QPS, pretty simple queries. So because this query structure is very simple, it is very hard for you to like write a query which will break the system, because the only safeguards you need is in a server. Okay, I'll say that there is like a minimal. So for example, let's say my proxy service is receiving these queries. Only thing it needs to look at is, okay, do you have a limit in the query? If you have a reasonable limit, let's say 100K, 1 million or whatever, then as long as we put a limit there on the maximum limit you can add, then my system is protected. Like you can just keep on sending and experimenting with queries. And you can have production traffic running on the existing tenant, and it's very hard to break the system. People can also like change queries easily without worrying about breaking the system. But once you start going into the general SQL realm, which is what the multi-stage engine allows. So the multi-stage engine was the engine we added back in 2023. It stabilized in 2024, and I think today like it is pretty much stable now. And what it allows you to do is like it allows you to like any arbitrary SQL query, which can read across any number of tables and do pretty much anything that you want it to do. But what that means is that let's say I have, for example, here a select on a given table, and then maybe I'm also doing a read on another table where, so I have something like this is a join. This will also incur like a full table scan if I don't have enough filters in there. So once you have something like this, then it is very hard to figure out how to make sure that people are not going to write a query which is just going to exceed the theoretical limit of the system. And this is a unique challenge to OLAP systems, which is not, for example, like Presto and Trino are also very mature in handling queries like this. But they can say that they're an interactive analytics system. So they can say that if you write a query like this, don't expect it to be run in like under a second. And it is because most of the queries have very relatively loose SLAs compared to Pinot, which is like a real-time serving stack. And in a serving stack, you always have like usually latency SLAs of like maybe like hundreds of milliseconds or 500 milliseconds or what have you. So if you're operating in that realm, then supporting this while you're supporting such a strict SLA and high QPS and low latency and like arbitrarily like increasing or decreasing data volume, then it becomes very hard to like support this feature. So what we realized was that we need to add like a new mode to Apache Pinot, which is taking the best of both worlds. So it is taking in the resiliency and the scatter gather intuitive nature of the single stage engine. At the same time, it doesn't limit people to just like running this. For example, at Uber, we have seen that it is pretty common for people to just run like one subquery, then another subquery, and so on and so forth. We also have talked about this in a couple of engineering blogs of ours. So we thought like, is there a simple way to support this in Pinot? And we recently added the support for multi-stage engine light mode, which essentially is another mode within the multi-stage engine. What it allows you to do is like with the multi-stage engine, a query like this would run in a scatter gather kind of with the multi-stage engine, a query like this would run with shuffles wherever it has to shuffle data. But with the multi-stage engine light mode, we essentially like do a scatter gather of any complicated query that you submit to us, and we'll truncate results. So essentially within the combine operator, we'll truncate around 100,000 or 1 million records. So that way your table scan problem is kind of solved, that we won't allow you to like scan a lot of data. And at the same time, the only problem the shuffle problem is also solved because we don't incur any shuffles because we do scatter gather. So the leaf stage is run in the servers and the brokers run the rest of the thing. I think we are out of time. This is probably going to be another talk in itself. But maybe I'll pause here and
yeah, I think it makes sense because we don't want to rush through some of the concepts because they are really deep concepts. There is a lot to talk about. But so far we have covered the basics, the high-level architecture, some of the important concepts in the ingestion path, and the single-stage query engine. So probably we should do another episode where we talk about the multi-query engine and the optimizations that go in. Also a little bit about indexing and the challenges. Yeah, I think for our viewers, if you like this episode, please share your feedback, like it, share it, subscribe to the channel, and also let us know what you want us to talk more about in the next episode that we are going to do on multi-stage query engines. So thanks a lot, Ankit. It was really clear explanation of all these concepts in a short time, but we should do it again for the next advanced topics.
Absolutely. Yeah. This was a pleasure.
Awesome. Thanks a lot.